Imagine this. Your laboratory process is perfect. 98% yield. Excellent purity. Every trial is successful. Now, you scale the same process, from a 5-liter reactor to a 5,000-liter reactor. Nothing changes. Same chemistry, same raw materials, same reaction temperature. Yet, your yield drops to 88%. What changed? The production team says, we followed the batch manufacturing record. Quality assurance says, raw materials passed every specification. R&D says, the chemistry worked perfectly in the laboratory. Everyone starts looking for the problem. Was it the raw material? No. Was it the reactor? No. Was it the chemistry? No. The real problem was something almost invisible. Mixing. One of the biggest misconceptions during scale-up is this. If we keep the same agitation speed, the mixing will remain the same. It sounds logical. Unfortunately, it is completely wrong. A laboratory reactor operating at 300 rpm does not behave like a commercial reactor operating at 300 rpm. Because rpm only tells us how fast the shaft rotates. It tells us nothing about how efficiently the liquid is actually mixed. This single misunderstanding has caused countless commercial batch failures. Let's forget chemical reactors for a moment. Imagine stirring a cup of tea. Just a few rotations with a spoon, and everything becomes uniform. Now imagine standing beside an Olympic swimming pool, using exactly the same spoon, making exactly the same motion. Will the entire pool mix? Of course not. Nothing changed. Same spoon, same movement, same person. The only thing that changed was the scale. Chemical reactors behave exactly the same way. As reactors become larger, moving every molecule becomes much more difficult. So, if RPM doesn't define mixing, what does? During scale-up, engineers focus on 6 important parameters. Flow pattern, power delivered into the liquid, pumping capacity, tip speed, blend time, and Reynolds number. These parameters determine how fluid actually moves inside the reactor. They help engineers predict whether mixing in a pilot plant will behave similarly inside a commercial reactor. And this is exactly where mixing scale-up becomes both an art and a science. In the next section, we'll go inside the reactor. We'll see why dead zones form, how poor circulation creates impurities, and how experienced process engineers use scale-up calculations to prevent commercial batch failures. Let's now go inside the reactor. When an impeller rotates, many people imagine the entire liquid moves uniformly. But that's not what actually happens. Inside every large reactor, there are regions where liquid circulates rapidly, and other regions where movement is very slow. These slow-moving regions are called dead zones. Imagine 2 molecules entering the reactor at the same time. One reaches the impeller within seconds. The other remains trapped near the wall or bottom for several minutes. Although both molecules are inside the same reactor, they experience completely different environments. And that's where scale-up problems begin. Let's consider a real industrial example. During laboratory development, the scientist adds 100 grams of catalyst into a 5-liter reactor. The magnetic stirrer disperses it almost immediately. Every part of the reactor receives nearly the same catalyst concentration. Now imagine the commercial plant. Instead of 100 grams, you are adding 100 kilograms. Even if the addition takes place over several minutes, the catalyst first accumulates near the addition point. Before it can disperse throughout the vessel, that region experiences a much higher catalyst concentration than the rest of the reactor. The reaction becomes faster locally. Heat generation increases. Side reactions begin. And impurities appear. The chemistry hasn't changed. The catalyst hasn't changed. Only the mixing environment has changed. Here's another example that many process engineers encounter. A reaction requires sodium hydroxide to adjust pH. In the laboratory, the quantity is small. The reactor mixes quickly. The pH becomes uniform within seconds. Now consider commercial production. Several hundred kilograms of sodium hydroxide are added. Before complete mixing occurs, the area near the addition nozzle reaches an extremely high pH. Some molecules are suddenly exposed to conditions they were never designed to withstand. The active pharmaceutical ingredient begins to degrade. New impurities form. Later, when samples are analyzed, everything appears normal because the reactor eventually becomes uniform. But the damage has already occurred. This is why experienced engineers focus not only on what is added, but also where, how, and how quickly it is added. After seeing these examples, it's easier to understand why RPM alone is not a reliable scale-up parameter. RPM simply tells us how many times the shaft rotates in 1 minute. It does not tell us how much liquid is being pumped, how much energy enters the reactor, how much shear is generated, or how long blending actually takes. Two reactors operating at the same RPM can have completely different mixing behavior. That's why process engineers use engineering parameters such as power per unit volume, tip speed, flow number, blend time, and Reynolds number. These parameters describe how the liquid behaves, not just how fast the motor turns. Now we know why mixing changes during scale-up. The next question is even more important. If engineers don't use RPM, what do they use? In the next section, we'll explore the engineering principles behind mixing scale-up. You'll learn why experienced process engineers talk about power per unit volume, tip speed, Reynolds number, blend time, and flow number, and how each one is used to design a successful commercial process. By now, we've established one important fact. RPM alone cannot predict mixing performance. So what do process engineers use? The answer is engineering scale-up criteria. Depending on the process, engineers may preserve power per unit volume, tip speed, blend time, Reynolds number, or pumping capacity. Notice something interesting. There isn't a single correct answer. Every process demands a different strategy. That's why agitation scale-up is considered both an engineering science and an engineering judgment. We've now understood why mixing changes during scale-up. The next question is even more important. How do experienced process engineers decide the correct scale-up strategy? The answer is surprisingly simple. It depends on the objective of the process. Let's look at a few examples. If you are blending two liquids, your objective is uniform concentration throughout the vessel. Here, blend time becomes the most important parameter. Now imagine a slurry reaction. The challenge isn't blending anymore. It's preventing solids from settling. Engineers therefore evaluate the just suspended speed, or NJS. NJS is the minimum impeller speed at which no particles remain on the reactor bottom. Once suspension is achieved, engineers verify that sufficient power per unit volume is available to keep the solids uniformly distributed. Now consider hydrogenation. Here, the objective is efficient gas dispersion. Hydrogen must be broken into thousands of tiny bubbles to maximize gas-liquid contact. For geometrically similar reactors, engineers often preserve tip speed because it influences shear and bubble breakup. Finally, think about crystallization. The objective is not just mixing. It is maintaining uniform supersaturation throughout the reactor. Poor circulation leads to localized nucleation, fine crystals, slow filtration, and poor product quality. The key lesson is this. There is no universal scale-up rule. The process determines what needs to be preserved. Let's take a practical example. Suppose you're carrying out a slurry reaction. In the laboratory, the quantity of solids is small. The magnetic stirrer keeps every particle suspended. The reaction proceeds uniformly. Now move to a commercial reactor. Several hundred kilograms of solids are charged. If the impeller cannot generate sufficient pumping capacity, the heavier particles begin settling at the bottom. The lower part of the reactor now contains excess reactant. The upper part becomes deficient. The result? Poor conversion, longer reaction time, lower yield. Notice something. The chemistry hasn't changed. The solids haven't changed. Only the mixing behavior has changed. That's why engineers verify suspension during pilot plant trials before moving to commercial production. Now let's consider hydrogenation. In the laboratory, hydrogen is dispersed efficiently throughout the reactor. Every catalyst particle receives hydrogen. The reaction finishes in 2 hours. At commercial scale, things change. Hydrogen still enters the reactor. But instead of dispersing uniformly, many bubbles rise directly to the surface. Large bubbles provide less surface area for mass transfer. Some catalyst particles receive very little hydrogen. The reaction slows dramatically. Engineers don't simply increase hydrogen pressure. They investigate mixing. They evaluate impeller design, gas flow, power input, and dispersion quality. Again, the chemistry hasn't changed. The mixing has. This is perhaps the most important slide of today's episode. Experienced process engineers don't start with formulas. They start with questions. What is controlling this process? Is it blending, solid suspension, gas dispersion, crystal growth, or heat removal? Once that answer is clear, choosing the appropriate scale-up criterion becomes much easier. This is exactly how technology transfer teams evaluate new processes before commercial manufacturing. Before we conclude, let's quickly summarize today's discussion. We learned that maintaining the same RPM does not guarantee the same mixing performance. As reactor size increases, fluid behavior changes. Every process has a different engineering objective. Some processes require rapid blending. Others require solid suspension. Some depend on gas dispersion, while others demand efficient heat removal. That's why there is no universal scale-up rule. A successful process engineer first identifies the controlling phenomenon and then selects the appropriate scale-up criterion. Finally, never underestimate the value of a pilot plant. It allows engineers to verify mixing behavior before risking an expensive commercial batch. Now it's your turn. Here's today's engineering quiz. Which parameter is most suitable for the scale-up of a solid suspension process? Option A, blend time. Option B, just suspended speed, or NJS. Option C, tip speed. Or option D, reactor volume. Pause the video, think like a process engineer, and share your answer in the comments. At the beginning of the next episode, I'll discuss the correct answer and explain why. Today we explored why mixing changes during scale-up, but another important question remains. If every process requires a different type of mixing, how do engineers select the right agitator? When should you choose an anchor? Thank you for watching PharmaChemE. If you found this episode useful, please like the video, share it with your colleagues, and subscribe to the channel. Your support helps us create more practical engineering content based on real industrial experience. And remember, chemistry creates the molecule, engineering makes it manufacturable. I'm Ankush Chopra, and I'll see you in the next episode.